Good afternoon and good morning, depending on where you are in the world, and welcome to DCD Keeping IT Cool, the only event dedicated to taking a deep dive into data center cooling technology and the challenges of managing higher density deployments. I'm Rebecca Davison, and I head up our conferences globally here at DCD, and I'm one of today's virtual chairs. I'm proud to be putting on this fantastic and free digital gathering for the industry at this challenging time, with most of the world still in lockdown and the global response to COVID-19 continuing. To those of you rejoining us, I hope you enjoyed the earlier sessions today, and to those of you for whom this is your first DCD Keeping IT Cool experience, welcome and thanks for being one of the 1,500 plus individual session viewers we're hosting over this week. This is actually our 9th virtual event this year and the last of our summer calendar of new virtual events. But don't worry, we have all of our regional events in virtual format to look forward to for the remainder of the year and to keep us going until our face-to-face events return in the summer 2021. They're free to view for the whole world, and since our first virtual event, DCD New York, back in the beginning of April, more than 15,000 people have tuned in, including this audience listening right now. As the most visited media partner in the sector, we want to be leading the way as ever in online content, networking, and best practice sharing. You can see the link to the full calendar below. All agendas will be coming soon, and you can register free now for any of conferences of your choice. There truly is something for everyone. The response and interaction we've had so far has been terrific, so thank you so much for being a part of that. It's worth also noting the new on-demand tab on datacenterdynamics.com, where you can delve into all of our presentations from the series at a time that suits you. So there's no aeroplanes, no queuing for conference halls, and don't worry, we've got networking covered too. Let me explain that now. A fantastic new addition to the DCD Virtual Event Series is our unique end-user networking platform powered by SwapCard. You can see the link to the platform in the resource widget labeled Network with Speakers and Delegates. This is only open to owner-operators, service providers, and AECs tuning in. You simply need to click the link and you can connect to other attendees and set up one-to-one meetings in the platform at the click of a button. You'll not only be able to find out who else is at the conference, but you'll be able to connect with them and even schedule one-to-one meetings with a fantastic inbuilt video conferencing option. You can filter through the delegate list and find peers who are facing similar challenges to yourself. And if you like what the speakers have to say, why not reach out to them and book an appointment to discuss things in more detail after their sessions. You just need to sign up for this in 2 easy steps if you haven't already. Click on the link in the resources section. It says Network with Speakers and Delegates, and then you'll see a home page for the app, and in the top right-hand corner it says Login, and there you just need to put in the email address for which you registered for the event with. The rest is very self-explanatory as the platform is really intuitive. We're using the OM24 webinar platform for this event. On the dashboard in front of you, you'll find the bios for today's speakers, web links to connect with them and join the next session, relevant papers to download, and a Q&A widget which you can use to put questions to our speakers. We'll try to fit them in as we go along. Also, be sure to share the sessions with your peers. All the sessions are being recorded and can be viewed on demand at www.datacenterdynamics.com immediately after the session finishes, so no problem if you've missed any. So on to the next session of the day. I'm pleased to introduce our next speakers for this joint presentation. Joining us we have Bill Krug, the President of OptiCool Technologies, and Jim Treadway, the Chief Engineer of IT at Mitre Corporation. As the President of OptiCool, Bill Krug brings nearly 40 years of experience in information technology, starting custom software development. Bill's career has spanned the gamut of project management, business operations, and sales. And Jim Treadway provides strategic and technical leadership to the Mitre Corporation Center for Information and Technology, delivering high-value capabilities in diverse areas of infrastructure, computing, networking, storage, and technical innovation. Bill and Jim are joining us today to present on pumped refrigerant active rear door solutions, meeting the needs of multi-density IT demands. And I would now like to welcome Bill and Jim to the virtual stage. Gentlemen, over to you.
Thanks for the introduction, Rebecca. We're very happy to be here today. We're all here to talk about how pump refrigerant in an active rear door solution is going to meet the needs of these multi-density IT demands. More specifically, what we have in this presentation that we'll be deep diving on is 3 case studies with actual customer production performance data that show in a high-density, multi-density environment the end result is a room-neutral solution, meaning the same degree air going in the front of the rack is coming out of the back of the rack. So everyone here at DCD this year understands today's growing IT cooling challenges. I mean, simply put, the pace of innovation and change in the contemporary IT arena is advancing much faster than in the data center industry, and there's a lot of applications that are driving that. So what's driving these higher and higher IT densities across the application landscape? Now here's a long list, and there's many more. I mean, everything from artificial intelligence, machine learning, blockchain. One application that we're going to be going through in great detail is one of our customers that's doing geomodeling and global imaging. Jim is actually going to go into some more detail on how is traditional cooling keeping up with this, and what are some of the challenges with traditional cooling in cooling these types of applications.
That's right, Bill. A lot of the activities happening in contemporary IT now are really driving our thermal densities much higher than traditional room-based cooling can handle. Even with containment, the reality today is that trying to support the higher densities of the kinds of compute environments that organizations are needing to run today is increasingly difficult to manage using traditional room and row-based cooling. So one of the key concepts that we really want to leave people with today is how advances in close-coupled cooling are really enabling IT to drive the types of technologies, use the types of technologies that we need to be effective. Most people are probably pretty familiar with the traditional density definitions that AFCON's had out there for quite some time, which fundamentally, is putting, 15 kW is considered a high-density environment. 5 years ago, that probably was, not too far off the mark. But contemporary IT has moved much farther beyond that. It is routine now for organizations to be running per cabinet densities in excess of 15 kW. Matter of fact, we're finding that organizations, and we're going to touch on this today, are going beyond that. So one of the key pieces really is understanding that traditional data centers have mostly been around a concept of room-based cooling. We're going to cool a large volume of air, and we're basically just going to treat the data center as a warehouse or a Walmart. It's fundamentally not a very effective model, particularly in the higher density ranges. Row-based cooling, in-row cooling has been out for quite some time. It certainly is capable of supporting higher densities than room cooling. It's not necessarily so cost-effective. Today, what we're really talking about is moving into that next range of technological maturity in terms of the cooling technologies and looking at rack-based cooling. And certainly there are lots of interesting things that are happening down at the component level, or touch cooling you'll hear referred to often. That's still a fairly nascent environment. It still feels pretty niche. It's still emergent. So today we're really going to focus in on rack-based cooling as the most efficient model to deliver close-coupled cooling to higher density and a larger range of multi-density IT workloads. So one of the key principles that is important to understand as we go through this today is that the problem statement fundamentally is how can organizations transfer heat energy out of the data center out into the atmosphere somehow. Fundamentally, that is the problem statement. How to move heat energy from point A to point B, and to do that most efficiently and most cost effectively. Air is free. Everybody gets that. It's easy to blow air around, but the reality is that air is not an efficient medium to transfer heat energy. Air is an insulator. It's not an efficient conductor. Water has been in people's data centers for years in various forms and fashions. And the reality is that water has a medium per unit volume can conduct about 3,400 times more heat energy than air can. But what most people don't realize is that moving to a two-phase cooling system using engineered substances like R134A, or introducing the kind of the term a vaporizable dielectric fluid, is a far more efficient way of moving heat energy than single-phase cooling with air and water. And so what really is happening, what we're going to really dig into today, is that a two-phase heat transfer system can carry about 9 times more heat energy than water can, or about 30,000 times more heat energy than air. And that concept, that principle, is what you will see as we go through today, is driving the substantial efficiencies and economies in a more modern approach to data center cooling.
So what does a close-coupled cooling solution look like? What we have here is a pump refrigerant, active rear door heat extraction layout. And one correction I'll make there is, while we claim to be the next generation in data center cooling, it is literally a heat extraction solution. It never lets the hot air make it out of the rack into the room. And what you'll see depicted in this layout is there's no hot aisle, there's no cold aisle. The racks are all pointing in the same direction, and the fans are pulling air from one end of the room to the other, a laminar airflow. And there's a lot of benefits for that. And the biggest benefit and the biggest theme of this is high density, multi-density. This layout is completely room neutral. In our data centers with our customers, they're running their ambient temperature between 75 and 76 degrees as opposed to, your conventional, we're in the 60-degree mark, because simply there's no need to cool the entire room. We're going to go into more detail on how all that works later. But the room is comfortable and quiet. It's mechanically simple. It's modular. It's scalable. Everything is quick connect. You can grow within the rack with no real construction costs. Again, low density and high density right in the next rack. It eliminates the need for raised floor, ceiling air plenums. Basically it increases capacity while decreasing the physical footprint. Now that we've gone through some of the business benefits of a pump refrigerant system in a room layout, I'm going to dig a little deeper here. How exactly are we removing heat from the rack? We use refrigerant pumps that flow refrigerant through a closed loop. We do not compress refrigerant. So that liquid refrigerant flows from a supply line into every one of our doors which attach to the back of any size rack. Inside of those doors, there's between 1 and 3 heat extractors with fans. Those fans are pulling hot air through the heat extractor from the inside of the rack. What happens on the outside of that door is we're blowing room neutral air. So that heat extractor is capturing the heat, and it's feeding the vaporized refrigerant that contains all of that heat back into the pump. And these pumps can do outdoor heat rejection to a chiller plant or directly to a DX unit. Jim's going to go into a little bit more detail on exactly what happens inside of that heat extraction unit.
So fundamentally, what the system is doing is we're capturing the heat in the cabinet. We're not allowing the heat to escape into the data center in the first place. This concept of micro-containment, if you think of the back of the IT gear, that cavity between the rear door and the equipment, that's your hot aisle. We're keeping all that heat energy in the cabinet. We don't let it come out into the occupied space at all. The heat extractors are essentially functioning to absorb all that heat and to do that very efficiently through a two-phase cooling effect. We're essentially boiling low-pressure liquid refrigerant in the heat extractors, converting that into a gas, about a 90% gas return that goes back to our pumps where it can be dissipated through other means out to a chiller plant or to a cooling tower or whatever you might want to be using. But that concept of keeping the heat in the cabinet, absorbing it into the heat exchangers, and efficiently moving that heat energy from the computer equipment all the way back to our external heat dissipation. That's what drives the efficiencies. We're able to absorb all of that heat and to reduce the cost of cooling dramatically, and we'll touch on that in a moment. So when we look at this type of technology and we really try to compare and contrast that to other methods of moving heat energy out of the data center, what we find is that air-based solutions pretty quickly fall off the radar. They're just simply not capable of efficiently or cost-effectively dealing with much higher densities and higher variabilities in densities. Our work about 5 years ago, when we were trying to figure out our best path forward, very quickly turned into a conversation around liquid cooling, water or refrigerant, and that turns into a conversation around whether you're doing in-row cooling, rear door cooling. There's a variety of solutions available, but what we found is that from a CapEx perspective, normalizing for a design goal of 200 kilowatts in 10 contiguous cabinets, or essentially 20 kW per cabinet, 10 cabinets, we find that the CapEx, the cost to implement this system is roughly about the same as doing in-row, only far more efficient. And that efficiency is manifested in the OpEx. The yellow graphs here, you'll see that the OpEx cost for that same 200 kilowatts of heat extraction is dramatically cheaper than any other method out there right now. And to take that one step farther, when we looked at this system and our deployments, and we compare and contrast to the options in terms of looking at colo opportunities, what we find is that this system is far more efficient than traditional crack-based environments. What this graph is showing is that the two green bars are showing the low and high water marks for the cost to operate at $1 per kilowatt per month at about 22 different colos that we got quotes from in Northern Virginia. And what we find is that by using two-phase pumped refrigerant technology, it's allowed us to reduce the cost of heat extraction in our data center by about 90%. And so what you'll see is that second graph with the gray, orange, and blue. The gray is the IT cost, the electrical cost of IT equipment. The orange is essentially the cost of the chiller plant and pumping to the data center. And blue was the cost of heat extraction through cracks. You'll notice in the far left graph, the crack cooling, the heat extraction cost in the data center is almost entirely eliminated. There's it's just a sliver. It's a 90% reduction in the cost of extracting heat. When you can look at that across the whole landscape of the cost to operate the data center, it's about a 20% overall reduction in cost, which is a tremendous cost savings. And so to take that a step further, one of our design goals when we retrofit our data center back in 2015 was being able to plan for future expansion, but doing that at a predictable cost function. Being able to scale up incrementally to accommodate new demand. So one of the key concepts behind all of this was not overbuilding for anticipated demand, but having the ability to modularly and efficiently add capacity, but at a predictable price point and at predictable performance metrics. So what we've basically described is that in this graph, the yellow line is showing increases in data center capacity in 250 kilowatt increments. And as this shows is that the blue and red lines are indicating that as we increase, as capacity has to go up in 250 kilowatt increments, the cost of traditional colo, blue being the high watermark, red being the lowest watermark, it's pretty clear that the cost of operating this system is dramatically less expensive, even as we add capacity incrementally in the future. And so what we've found is that this type of technology, because just the nature of the technology, allows us to find efficiencies and economies that can support IT's needs in the future without having to make major capital investments again and again and again. So to take this a step further, we wanted to go through some different scenarios, some different use cases of how this is actually being applied in the real world. And so we've got a few scenarios that we want to step through. The first really is looking at a very classic enterprise IT kind of scenario, blade computing, heavy virtualization. What we've basically done is captured more precise data of what's actually happening in this model. The punchline really is that when you look at the intake temperatures that we're running them, as Bill mentioned, we're trying to keep the rooms around 75, 76 degrees. Even though we have elevated internal temperatures, the exhaust coming out of our server gear, in this case, it's around 100 degrees, the important point is that even though we're running at about 12.5 kilowatts per cabinet, in the bottom graph you see kind of a relatively sustained load, the important point is that the upper graph showing you the blue and green, the blue line is showing the intake room temperature, and the important point, the real punchline of this system is that the exhaust temperature, the green line that's coming out of the cabinet, coming out of the heat extractors, is actually half a degree to a degree cooler than the room temperature coming in the front of the cabinet. That concept of room neutrality is critical to how we're driving the efficiencies of this system. So if we take a look at a different IT scenario, in this case looking at a fairly higher density mid-scale Hadoop cluster, it's quite a bit different from the virtualization platform we saw a moment ago that had relatively stable power loads. When you start getting into some more advanced analytics, oftentimes you'll find that the power loads can be much more variable than people anticipate. Hadoop clusters, just their very nature is that they tend to sit idle while you're prepping for some type of analytics run. But once you initiate that run, the loads can be quite high. So these Hadoop clusters have a broader range of power loads and obviously heat outputs that are often difficult to handle with traditional data centers. That variability, that high swings of load is quite challenging. And so the point here really is that even with these higher power loads, in this case, somewhere between 15 and 18 kilowatts per cabinet, the point really is that by capturing the heat in the cabinet and extracting that directly into an engineered medium, we're able to still get the same result that we had with the other scenarios, where the output temperature coming out of the cabinet is about a half a degree to 1 degree cooler than the intake. And that's a really critical takeaway. So looking at a third scenario where we have dramatically elevated power densities, we're looking at here an example of a company in Northern Virginia called Vricon that is also operating pumped refrigerant rear doors. Here they're running multiple contiguous cabinets of about 30 kilowatts each. And in this environment, what we're still finding is that the end result of two-phase active rear door cooling, we're still able to maintain an exhaust temperature that is about half a degree to 1 degree cooler than the intake temperature in the room, which again is around 75, 76 degrees. There's actually going to be a deeper dive into this in late August at the DCW conference and take a much closer look at what Vricon has been doing with much more advanced analytic capacities and how they're finding economies in power and cooling. And so what we've really been trying to describe is that the diverse needs of contemporary IT have changed a lot in just the past several years. And there's really a need for a next generation type of data center. We need a different type of data center that can allow IT to make the advances that we need to deliver on our mission. And some of the characteristics that we really are describing that we need is support of multi-density, not just high density, but highly variable density. We need modularity, the ability to move workloads across the data center and not have to deal with hot spots or moving in-row cooling, but the idea that I can move my cooling solution to the cabinet where I have elevated loads and do that incrementally is a tremendously powerful mechanism for IT. At the end of the day, what we're describing is a shift, finally, to some forms of liquid cooling. It simply is more efficient. It's indisputable that two-phase cooling is far more efficient than single-phase cooling. It's less expensive to operate, it's more efficient, and it really enables a lot of economies for IT. This micro-containment concept of keeping the heat in the cabinet, don't let it out in the room in the first place, that is a critical concept that needs to really be adhered to moving forward. Finding more efficiencies in power transformation as we increase our cooling densities required in the cabinet, 20, 30, 40 kW. You also have to be able to deliver, 20, 30, 40 kilowatts of power to a cabinet. That's not so easy to do sometimes. Ultimately, what we really want to see is that the costs, the CapEx and the OpEx of supporting higher density, higher variable density IT loads, that's really what IT needs in the next generation of data center partners.
So we just reviewed Vricon's data for their high density application, which happens to be driven by one of those earlier drivers that we talked about, global imaging and analytics. It's very, very high compute applications. So this row that you're seeing on the right is a true high-density, multi-density row. There's 10 racks at 30 kW in that picture, and at the end of the row, there are 3 low-density racks. They're only running between 3 and 5 kW. Those particular racks, you could put them in between any of the high-density racks. You can mix and match, and it really gives you the ability, this whole concept of multi-density. You could start out with a 5 kW rack down at the end there, but if next month your IT group rolls out an application that's high compute, you add more heat extractors. There's no construction cost to make this happen. So another amazing example of this type of system and the energy savings that it really delivers to our customers is down in San Antonio at a big customer of ours, CPS Energy. They designed their brand new data center in 2015, and it was designed around our product. And one of the biggest drivers in this particular scenario was the energy savings. So the building is certified LEED Gold. And one thing that we didn't really mention in this entire presentation are, what are all of the benefits of energy reduction? So, you're cutting your carbon footprint. There's cash savings. But then in today's world, most energy delivery companies have dramatic rebates for anything that you can do in your business to reduce energy. We're seeing our customers receive upwards of 30% cash rebates on the CapEx on the equipment. CPS Energy does that on a regular basis. We have other customers in the general area that have received those rebates. So to kind of summarize and wrap things up, what does close-coupled pump refrigerant systems really do for you? Well, we've hit on all of them, but capacity. You can run low to high density in this particular system, upwards of 60 kW per rack. It's very adaptable, whether it's a new build or retrofit. These cool doors can fit just about any IT or telco equipment rack. And it's really the only system on the market that has scalable cooling. The modular design really gives you unparalleled scalability, as needed cooling. Energy efficiency, we just hit on that, all the benefits of that. And then space efficiency, again, we're densifying. You're using less space. Some of our customers avoid capital costs because they can't densify without our solution, so they have to do more build-outs. So this is the perfect type of solution for edge deployments, IT closets, MDF rooms, or as you saw with the CPS Energy example, very large data centers. That concludes this part of the presentation. Our contact information is up on the screen. You contact us anytime to do a deeper dive on this type of technology. Right now, we're going to turn it back over to Rebecca for questions and answers.
Thank you so much to both of you there for a great presentation and for sharing your insights and time with us today. Yeah, we covered a lot of ground there. It was really interesting. Thank you. We've now got a little bit of time for some questions from the audience, and I've seen a few of those have come through. So let's try and get through as many of those as we can right now. Now, let me see. First question here. How do you control humidity?
Yeah, humidity. That's a great question that comes up often. We found that actually it was a pretty simple problem to manage. We chose not to try to use cracks to perform any dehumidification functions. Frankly, the cracks aren't very efficient at that. We actually found much smaller, less expensive, and more efficient methods to manage the humidity from makeup air infiltration and general room infiltration, and not having to go through extreme measures to, try to hermetically seal the data center. So we actually wound up using a pair of high E 195 dehumidifiers. They're very inexpensive, and they actually were very efficient, far more efficient than trying to use traditional crack-based dehumidification. Low cost to operate, very small, compact. It actually turned out to be a much better way of managing humidity in the data center than traditional methods.
Great, thank you. Okay, so next question here. Can you connect to the BMS?
Absolutely. So we've got connections and APIs that will connect to a Modbus system or BACnet. And that would allow us to push all of the data that's being monitored within that pump. It's fully integratable.
Fantastic. Right, we've got an interesting question here. What happens if it leaks?
Great question. We get asked that a lot. So unlike water, with our system, in the extremely rare event that there would be some type of micro leak, the R134 refrigerant is non-toxic, it's non-corrosive, and it's non-conductive, so there really isn't any impact to the IT equipment. It's very safe.
Great. Okay, and I think we've got time for one more question here, another interesting one. Can I replace my in-row cooling with your solution?
Absolutely, yes. So what we see out there is most of those in-row cooling solutions are running off of chilled water. So if you are running into those types of densities where our solution is a better fit, you could simply remove those units, and what you've seen in some of our layouts is the mini pump solution. You could roll the mini pump, which is only 15 inches wide, right up to the end of that row. Plug in your plug-and-play refrigerant hoses and the network, and you're good to go.
Great. Well, I think that's all the questions we've got time for right now. So that just leaves me to say a very big thank you to Bill and Jim for your time and your insights today. And it's been a pleasure hosting you.
Thanks, Rebecca. And the pleasure was ours. As you can see, we are very excited about this technology. We're always available by phone or email or our website to answer any deeper level questions.
Yes, and if you did have any further questions for Bill and Jim, please do jump on SwapCard, our networking platform, and connect with them on there. You can set up a video meeting with them. You can continue the conversation and dig further into what they've been sharing with us today. Now, in just under 25 minutes, we have our final discussion of the event, focusing on the future of cooling and where that's heading. We've got some experts joining us from Equinix, NVIDIA, Villanova University, and moderated by our own George Rocket. So I hope you can join us in 25 minutes.